Looking through the bars of a shark cage and into the black eyes of a great white shark is not the time to wonder, sturdy is this cage anyway? You'll want to be certain of that answer long before you leave dry land. Our intrepid designer Jacques has just spent an entire week watching shark documentaries from the comfort of his own home. Feeling inspired, Jacques has decided that it's time to cash in his vacation time for a trip of a lifetime to Shark Alley, home to the highest concentration of great whites on the planet. But Jacques is not content to watch great white sharks from the surface. He wants to get up close and personal with the ocean's perfect predator. To get there, Jacques has decided to design and build his own submersible anti-shark cage. That's right, the cage goes in the water, Jacques goes in the water, and the shark is waiting in the water. And our shark, we'll call him Bruce, wants to swallow you whole. Like all good designers, Jacques wants to make sure his shark cage is fit for purpose. His holiday would be seriously ruined if a great white shark managed to get into the cage with him. So Jacques turns to SOLIDWORKS Simulation to make sure he'll be safe in the water. To ensure he's not reduced to chum, Jacques will test two potentially fatal shark attacks. 1. Sharks have a reputation of ramming cages with massive force. Jacques' design must protect him from being rammed at a high velocity. 2. Sharks also have a reputation for their strong jaws. Jacques' cage cannot buckle under the pressure of Bruce's powerful jaws clamping down on the bars. Jacques designs his initial shark cage making use of standard steel box sections he has lying around his tool shed. His documentary watching has revealed that the largest great white sharks weigh in at about 3.5 tons and can swim up to 35 miles per hour. So for the first test case, the shark ramming attack, Jacques decides that he only needs to include the front part of the shark, as this is the only area of the shark likely to impact the cage. This will simplify his analysis considerably. Jacques assumes that Bruce will hit the cage at its weakest point, dead center in the section without vertical bars. This gives Jacques a worst-case loading scenario and allows him to use symmetry to reduce his model size and runtime. Jacques creates a non-linear dynamic analysis to calculate how effective his cage is at stopping Bruce's charge. Jacques assumes his cage is made from standard structural steel S355 and has given Bruce the effective mass of a full-blown 3.5-ton shark. The cage is restrained at the top corners and the back face, as if the cage was supported by a hoist, resting against the dive boat, while Bruce is restrained to allow him to only move directly towards or away from the cage. Bruce is positioned just outside the cage, and Jacques defines contact between the likely impact areas between the shark and the cage. And finally, Bruce is given an initial speed of 15.65 meters per second, or 35 miles per hour. Jacques is now ready to run the analysis and review the results. Jacques sets the stress scale to show all yielded materials in red. The horror! Jacques is fish food. The amount and location of yielded material indicates the cage would likely break at the welds. The cage and Jacques would not survive a direct impact from Bruce. Jacques, you're going to need a stronger cage. Although Jacques knows he must redesign his cage if he wants to survive, he wants to see how effective his original design will be against a shark bite. Jacques' extensive television research shows that a great white shark can bite with the force of 18,000 newtons. For this analysis, Jacques doesn't need Bruce. He can simply estimate the bite area on the cage bars and create patches on the bars to which the bite force can be applied. Jacques assumes that the bite happens for a prolonged period of time, so he creates a linear static analysis. Jacques applies the same material and restraints as in the ramming attack and applies two opposing forces to simulate the effect of Bruce's jaws crushing the cage. He then meshes the model and, with some trepidation, runs the analysis. The outcome for the cage is much better for the bite attack than the ramming analysis. Bruce can smile all he wants, but Jacques' initial cage design would survive the bite force of even the largest great white shark. With the survival of the cage against a shark bite attack verified, Jacques refocuses on surviving a shark impact. He needs to improve the strength of his cage considerably. However, Jacques must keep the weight increase as low as possible, as he doesn't want the dive boat to roll over while lowering his cage into the water. Jacques begins by upgrading the main structural members with 100 by 100 by 10 mm square hollow sections and, although expensive, he opts to use titanium rather than steel material because of its vastly superior strength. Since the initial design performed well against the bite-crushing load, Jacques only needs to rerun the impact analysis. He duplicates his initial non-linear analysis, updates the geometry, and hits run. This time, the upgraded cage holds. The stresses are still high, but the new cage can successfully withstand Bruce's 3.5-ton charge at full speed. The anti-shark cage is now ready to go into the sea. However, after recent cinematic revelations, he's a bit nervous about weather affecting the situation. Jacques is going to prepare for the worst. He needs to answer the ultimate shark attack question. How will this cage react to being hit by a shark propelled at tornado speeds? Once again, Jacques duplicates the non-linear study and increases the ramming speed to 89 meters per second, or 200 miles per hour. Flying through the ocean as fast as a spinning tornado, Bruce the shark punches through the new titanium cage as if it were made of plastic. The impact is so extreme, the cage is permanently deformed and Jacques permanently scarred. Luckily for Jacques, this scenario would only happen in made-for-television movies. If he is still worried, he can always bring along a chainsaw. We've had fun with Jacques and his anti-shark cage, but we chose this scenario to demonstrate what SOLIDWORKS Simulation can help you achieve when designing your products. All companies can benefit from early warnings of possible performance or safety issues. The SOLIDWORKS Simulation provides advanced tools to solve your most challenging design problems. SOLIDWORKS Simulation makes it easy to see and understand how your products will perform under real-world conditions without having to build expensive and time-consuming prototypes. SOLIDWORKS Simulation gives you vital information that can help you make good engineering and design decisions, making your products better and your customers more satisfied. To find out more about SOLIDWORKS simulation tools, contact your local SOLIDWORKS reseller or visit solidworks.com/simulation. And remember, with SOLIDWORKS Simulation, you won't think it's safe to go back in the water. You'll know it.